Recording in progress. Okay, so this is homework 3, part C, right? So we're going to be looking at this tank here, right? We're going to have water in the bottom, liquid water. Up top, flowing across, we will have dry nitrogen, pure dry nitrogen, right? And this will be capped, right? So what this does is it makes there to be no pressure difference, so no pressure gradient, right? No pressure gradient, right? And then in this middle section here, we have an N2H2O mixture, right? Our nitrogen water mixture. The distance here will be 0 to L. That is not an L. In the positive direction, being upwards, right? So when we have done this past, we've looked at diffusion, right? So how did we do diffusion? We used Fick's law, right? Well, what's Fick's law? We have our J equals our concentration, right? Our negative concentration times our diffusion, and the driving force for Fick's law, right? That is our concentration gradient, right? Our dx1 dz, right? So as our concentration changes, our diffusion changes, right? Now this is just a fixed number that depends on whether it's a water, a gas, a solid, all that. And then when we look at concentration, well, we know in this case we'll be looking at molarity, right? So it's moles per liter, right? Well, what is moles per liter, right? That is N over V. Well, when we look at the ideal gas law, right, PV equals nRT. Well, when we solve for N over V, we get P over RT. So that means that concentration can be written as pressure over RT, right? So if we're looking at our total concentration, we can write it as P over RT plus P over RT, right? One being for our nitrogen, the other for our water, right? So when we right, we look at this and we know that our concentration is our driving force, right? Our concentration driving force. So let's look at our concentration, right? If we are like looking, like we're diffusing upwards, correct? So when we look at this, we know that the concentration of water is going to decrease, right? Because we have pure dry nitrogen up top, right? This is dry, right? So that means that there's no water up there, right? And so when we look at, if we try and graph our concentration here, concentration over our distance, right? So 0 to L, right? Our highest point of water is going to be the pure water at the bottom, right? And we steadily decrease to basically 0 as we get up to L, right? Because we have dry nitrogen, as it goes up, we diffuse less and less, right? And so when we're looking at diffusion, typically we think, right, at our L point, that's where our highest content of nitrogen is, and we are going to decrease, right? But when we look at this, as we go down, this nitrogen has nowhere to go, right? So it has to go across here because it's not going to diffuse into the water, right? And so when we see this, this doesn't exactly work, right? Because now we're confusing diffusion with total molar flux, right? And so when we look at this, right, so Fick's law, let's rewrite this here. J equals minus C D dx over dz, right? And when we look at molar flux, right, we know that N, right, our total molar flux, equals, we'll say N1, right, equals our J1 plus our Y1, which is our vapor phase concentration, times our total molar flux. Well, what's our total molar flux? N equals the sum of our individual fluxes, right? So N1 plus N2. Now, when we look at this, we know that water has a positive flux, right? It's going up, it's diffusing up. But when we look at nitrogen, it's a little confusing, right? We look at nitrogen, and we're going to use the analogy of, let's say we're swimming, right? We're swimming in the ocean, and the waves are crashing into the shore, right? But we don't want to move, right? So you're going to stand there. You're not going anywhere, right? But you are exerting a force against the waves to keep you in that spot, right? So you are not moving, right? So our total flux is 0, but it is in the positive direction because we are exerting the force against it, right? And so if we're looking at a cup here, right, our water diffuses up, right? So we have our positive flux, but our nitrogen can't go anywhere. So it equals 0, but it is still positive, right? Right. And so we know that our N for our N2, right? Our flux for our N2 equals 0 because we're not going anywhere. The N2 has nowhere to go in this scenario, so it can't have a flux. Right? So when we look at this, if we rewrite this equation, equals J1 plus Y1, and then we can sub in our NH2O plus our NN2, right? Well, this equals 0. This equals 0. So that allows us to write the equation J1 equals Y1 times NH2O, right? And this is a very powerful equation because we can then use it with our fixed law, or we can use fixed law with it to then further solve problems where our gas is not diffusing into our liquid, right? So if we look at a example here, I'm going to go to a fresh page. So we're in kind of the same scenario, right? We have our tank or jar, whatever you want to call it. We have our nitrogen flowing across the top, right? Our water in the bottom here. And then our mixture, right? So in this equation, or in this example, what we're doing is we're going from a height of 0 to a height of 1, right? Our temperature for this equation equals 50 degrees Celsius. Now that is 323 Kelvin, right? We want it in SI units. Our pressure, which we are at steady state, right? With our cap here, right? So no pressure change, so that means this equals, with that, we only have one pressure of 1 bar, or 1.013 times 10 to the negative fifth, times 10 to the fifth pascals, right? So that's also in SI units. For gases, right, our diffusivity constant, right, from our fixed law is just going to be 10 to the minus 5. So what we want to do here is we want to figure out the flux for water, right? So what we just determined down here, right, we talked about our flux. We want to find that for our water, right, in this equation, or in this example. So where do we start, right? Well, we can write down a couple of equations, right? We know fixed law, right? That J equals CD minus CD, sorry. And then we're looking at the gas, so we're going to dy1 over dz. Then we have our flux, right? So NH2O equals our JH2O plus YH2O times our total N, right? So this is just the equations that we talked about a little bit ago. And so where do we want to start here? Well, we look at this, we can break this down a little bit, right? This N just equals NH2O plus NN2, right? We know that, right? So this is rewritten as YH2O times that plus JH2O equals NH2O, right? We can rewrite Fick's law down here. J equals minus P over RT, right? That's our concentration that we talked about in the last part. D, dy, dz, right? That's just, I moved the D into the numerator of the concentration because we're multiplying, right? So we can now plug this in here, right? So it's NH2O equals negative PD over RT, right? Our pressure times our diffusivity over our temperature, plus our concentration, times our DYH2O, right? Got to finish off this, over DZ, plus our YH2O times, now, and right, we talked about this a little bit ago, right? This just equals 0 here, right? Because this nitrogen has nowhere to diffuse to, right? It's just going to go around and around, right? So that's 0. So this ends up being YH2O times NH2O. Now, we're solving for NH2O. So I want to bring this over here, right? So we get our flux of our water times 1 minus Y water equals minus PD over RT dy water dz, right? And so this is our equation. Now what we want to do from here is we want to integrate, right? We have our differential here. We want to integrate to get rid of this, right? And so before we do that, we have to look at our pressure here, right? So our pressure is not our total pressure. It is our pressure for our water, right? Because we're looking specifically at our flux of our water. And so we want our partial pressure here. So how do we find partial pressure? Well, we know that our concentration, right, our YH2O equals our partial pressure over our pressure, right? And when we look at our partial pressure, this is, right, we can do a couple of things to get our pressure, right? Our partial pressure. There's, for substances that are not as commonly known as water, right? And you want to find it and you can't find it somewhere, right? You can either use the Antoine's equation, or you can use the Clapeyron equation. Now, these will both get you to your partial pressure using your temperature, your pressures, and constants if you're using Antoine's equation. But for a substance such as water, right, it is super commonly known, or it is super commonly used, so it has been experimentally found, and so you can just look it up, right? So our partial pressure of water, that looks like a density, right? So our partial pressure of water just equals 12 times 10 to the third pascals, right? Now this is specifically at 323 Kelvin, right? Because it'll vary depending on the temperature that you're at, and we are at 323 Kelvin, right? And so now we can go back to our equation for our concentration, right? So our Y H2O equals our 12 times 10 to the third pascals over our 1.013 times 10 to the fifth times 10 to the fifth, right? And so with this gets us about 0.12. Now, why is this important? Why do we need this? We're going to integrate this, and we don't have bounds for our concentration before we found that value, right? So now we know that this is our bottom bound. This is our bound at 0, right? So this is 0.12, and up here we know that it's dry nitrogen, so it's going to be 0. So now that we know both our partial pressure and our bounds for our concentration, we can then manipulate this equation. We'll bring this over and we'll bring this over, right? So we'll get our flux of our water times our change in distance equals our minus PD over RT times our DYH2O over 1 minus YH2O, right? And from here we can integrate. Well, we're at steady state, right? So there's going to be no change in our pressure, right? So our flux has to be constant, right? Because we're only varying by concentration, right? So this value will be a constant value until we can integrate before that, right? And that is from our 0 to 1, right? Our change in distance, 0 to 1. And then on this side, I'll rewrite this. So we'll have our NH2O times the integral dz from 0 to 1. And then we know that our pressure, diffusivity, R and T, those are all constant, right? Those were defined at the beginning of the problem, or we just found them, right? So that'll equal negative PD over RT times the integral from 0.12, right? That's the value we just found, to 0, because we are ending at dry nitrogen, of 1 over 1 minus YH2O times our DYH2O. Okay, so when we integrate here, we know that this is just NH2O times 1, right? Easy. And then over here, right, this is constant. And then we know that 1 over some value is the integral of that. It's just the natural log of what it's over, right? So ln of the absolute value of 1 minus YH2O evaluated from 0.12 to 0. Now what I'm going to do here is I'm going to bring this negative in, and then we'll flip that. And so we'll be left with NH2O equals PD over RT natural log of YH2O minus 1 from 0.12 to 0. So when we do this, I'm just going to calculate this, right? So this is NH2O equals PD, that is a PP, PD over RT. And then when we evaluate this, it ends up being the natural log of 1 over 0.88. And from here, we have all our values, right? So we're going to plug in, right? So I'll bring it a little bit out here. NH2O equals. So what was our pressure, right? That's our value up here. Our 12 times 10 to the third pascals. Our diffusivity, which is 10 to the negative fifth, and I didn't write it up there, but it is meters squared per second. And then over RT, right? So it's our 8.314 joules per kilogram Kelvin. Nope, meter Kelvin, I think. Times our temperature, which is 323 Kelvin, times ln of 1.88, 1 over 0.88, right? So what we will do here is we will pull out the trusty calculator and plug this in, right? So 12 times 10 to the third times 10 to the negative fifth over 8.314 times 323 times the natural log of 1 over 0.88. And that gets us 5.71 times 10 to the negative 6, right? And this is actually the wrong value, because when we're looking at the overall pressure, right, we don't want to use the partial pressure anymore. We're looking at the overall pressure. So it is 1 times 10 to the fifth. And so we can redo this 1 times 10 to the fifth, and we get 4.76 times 10 to the negative fifth, right? And what will our units be? Well, when we work all this out, it will be moles per meter square second. And so that is our final answer for what the flux of hydrogen, or the flux of water is in this problem. And so you can see we kind of used all of our equations, right? We had our fixed law, which we implemented into our flux equation. And then we had, well, we could have used our Clausius-Clapeyron or Antoine's equation, but instead we just looked it up. And we used that to find our bounds. And then we used our first equation and just plugged in, right? As simple as plugging in to get 4.76 times 10 to the negative fifth moles per meter square second.